Good afternoon, everyone, and thank you for joining us for today's webinar. We are going to get started here in just a few minutes, but before we do, I would like to go over a few housekeeping items with those of you that have joined us. For those of you that we do have in the room, the first thing I would like to make mention of is our chat pod, which is going to be located on the left-hand side of your screen marked chat. This chat pod will be the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained until the Q&A session that will be held at the very end of today's webinar. So please feel free at any time of today's presentation to go ahead and type in your questions there. We would hate for you to forget them, and then we will pull them out and house them for you, and we will hold them until the Q&A session that will be held at the very end of today's presentation. This chat pod is also the best way to communicate with us should you experience any technical issues. If you do have any technical issues, please make sure to let us know there in the chat pod, and either myself or one of our customer service representatives will make sure to get you taken care of. All of your audio for today's webinar is going to be streaming through your computer speakers. So if at any point during today's presentation you either lose your live audio or live video feed, the first thing we would like you to do to troubleshoot is simply refresh your web browser and then click the play button again in the middle of your screen. Doug, I see your comment there about the play button. It is either going to be located in the middle of your screen, or some users might need to expand the live video feed to full screen, and then you will see the play button either come up in the middle or it will also populate in the bottom right corner. That all depends on your web browser, the versions that you might be using, or the age of your device. So check those few locations out, and then if you are not able to find it, again, please let us know in the chat pod and we will definitely get you taken care of. Just going through a few things before we do get started. You will also see directly below our live feed that we do have closed captions that will be running throughout today's event. So if you would like to refer to that at any time, please feel free to do so below the live event feed. If for some reason your chat pod is having issues and you're not able to contact us there, or you would like to, you would prefer to reach out to us in another method, we also have our toll-free number as well as our email address that are going to be located directly above the live feed window for today's presentation. So again, if you do experience any technical issues, please make sure to use one of those methods to let us know. We've got about 6 or 7 minutes before we do get started. So before we do start today's webinar, we always like to find out a little bit more about our audience. We have quite a large registration number today. So if you could take a few moments and utilize that chat pod on the left-hand side of your screen and let us know where you are viewing today's webinar. That'll give us some great feedback about today's audience as well as the kind of reach we were able to obtain with today's event. We've got, again, about 6 minutes before we get started. I'm going to mute my line back for now, but I'll come on once more and we'll go through housekeeping one more time before we do get started at the top of the hour. Thank you for joining us today. Good afternoon, everyone, and thank you for joining us for today's webinar. We are going to get started here in just a couple of minutes, but before we do, I would like to go over a few housekeeping items with those of you that have just joined us in the room. For those of you that did just come into the room, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod will be the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained until the Q&A session that will be held at the very end of today's webinar. So please feel free at any point of today's topic discussion to go ahead and type in your questions there in the chat pod, and we will pull them out and house them for you, and then we will get them asked of our subject matter experts once the presentation has ended. This chat pod is also the best way to communicate with us should you experience any technical issues. If you do have any technical issues, please make sure to let us know there in the chat pod, and either myself or one of our customer service representatives will make sure to get you taken care of. I apologize for that. If at any point of today's live event you either lose your live audio or your live video feed, the best thing that we can recommend to troubleshoot is to refresh your web browser and then come back to the live feed play button. And once you hit the play button, again, that should refresh your both video and audio connection for today's event. If for some reason that does not work or you experience any other technical issues, again, you can utilize the chat pod, or you can also use the toll-free number or the email address that we have located directly above our live feed window. You will also notice directly below the live feed window that we do have our closed captions running throughout today's event. So if you'd like to refer to those closed captions at any point, please feel free to do so. It is the top of the hour, so we are going to go ahead and get started. But for those of you that have not typed in your location there in the chat pod, we would definitely like to find out a little bit more about our audience who is joining us today. We have some international presence that I've seen. I did see one from Poland as well as Puerto Rico and Costa Rica. And then we also have various locations spread out throughout the United States. We have quite a large group that will be joining us today, so we are definitely excited about your attendance as well as today's presentation. Again, it is the top of the hour, so I'm going to mute my line and shift some things around on my end, and then we will get started here momentarily. Thank you for joining us today. Good afternoon, everyone, and thank you for joining us for today's webinar. My name is Josh Vickers, and I will be your host and moderator for today's event. I'm with the Forensic Technology Center of Excellence at RTI International. Today's event is entitled Rapid and Effective Identification of Organic and Inorganic Gunshot Residues. Our first speaker that I would like to introduce today is Dr. Tatiana Trejos. She is an assistant professor of the Department of Forensic and Investigative Sciences at West Virginia University. Dr. Trejos teaches forensic chemistry and research design courses at the undergraduate and graduate levels. Dr. Trejos' primary research interests include the application of chemometrics to evidence interpretation and the discovery of chemical signatures of forensic materials by spectroscopic methods. She has authored over 35 peer-reviewed scientific publications and book chapters in the field of forensic chemistry and has presented over 140 oral presentations and posters at scientific meetings worldwide. Dr. Trejos was also appointed by NIST to serve as a member of the Materials Trace Subcommittee within the Organization of Scientific Area Committees, or OSAC, where she currently serves as chair of the Glass Task Group and member of the Interpretation, Research, and Physical Fit groups. Our second presenter of the day I'd like to introduce is Dr. Luis Arroyo. He's an assistant professor at the Department of Forensic and Investigative Sciences at West Virginia University as well. Dr. Arroyo teaches graduate and undergraduate courses in forensic chemistry as well as forensic toxicology. Dr. Arroyo's primary research focus on the characterization and analysis of emerging drugs of abuse, pollutants, environmental stressors, and gunshot residues. Dr. Arroyo has authored several peer-reviewed scientific publications, as well as presented over 70 presentations and posters at scientific meetings in North, Central, and South America, Europe, as well as Australia. The National Institute of Justice also has recently funded Dr. Arroyo's research in novel psychoactive substances and gunshot residues. Our last presenter of the day, unfortunately, is not going to be able to join us, but we want to make sure that her professionalism and contributions to the research is well known to our audience. So I'd like to introduce Dr. Suzanne Bell. She is an emeritus professor and former chair of the Department of Forensic and Investigative Science at West Virginia University. Dr. Bell's research expertise include the organic gunshot residue and explosive characterization with linked field instruments. Dr. Bell earned her Bachelor's of Science degree in Chemistry and Criminal Justice from Northern Arizona University, her Master's in Forensic Science from the University of New Haven, and then her PhD in Analytical Chemistry from New Mexico State University. She worked for 3 years with the New Mexico State Police Crime Lab as a forensic chemist, drug analyst, arson analyst, and crime scene investigator before joining the faculty of the C. Eugene Bennett Department of Chemistry at West Virginia University in 2003. Dr. Bell is the author of several publications, including 6 forensic science books, and was awarded several honors during her distinguished career. She served on the National Commission on Forensic Science, Research, and Scientific Inquiry Subcommittee, as well as the NIST Organization of Scientific Area Committees for Gunshot Residue. Just our quick disclaimer, the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenters and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. And now, without any further ado, I would like to hand the microphone and platform over to our first speaker of the day, Dr. Tatiana Trejos. Dr. Trejos?
Thank you, Josh, for the introduction. It's my pleasure to be presenting today. Good afternoon, everyone. It's a pleasure to participate in this webinar today and have the opportunity to present some of our gunshot residue research at West Virginia University. Give me 1 second. This work
Dr. Trejos, I don't mean to interrupt. It looks like you have a reminder that's over the bottom right corner of your screen.
Oh, thank you.
Perfect. Thank you.
Okay, thank you very much. So this work could not have been possible without the support of many individuals, so I would like to start by acknowledging them. And I warn you, there will be lots of people to thank, so please bear with me. First, I would like to thank RTI, the Forensic Technology Center of Excellence, and the National Institute of Justice for making possible the dissemination of this webinar. For some reason, it's not letting me pass the slides, Josh.
Okay. Maybe since I took control over, you might need to escape out of your presentation.
Okay, give me 1 second.
Escape out of the full screen mode and then go back into it.
Okay, give me 1 second.
There you go. That looks right.
All right, sorry about that. So this research is NIJ funded. So first I have to say that the opinions, findings, and conclusions are ours and do not necessarily reflect those of the Department of Justice. We are very grateful for the NIJ support that we have received. We were very fortunate to receive NIJ funding last year for the development and validation of fast screening methods for the detection of gunshot residues. NIJ also launches the career of many students, and their fellowship is one of many ways they make a big impact in our future professionals. We are honored to have received 2 fellowships, one last year for the characterization of modern ammunition, and one this year for the validation of LCMS methods for detection of organic and inorganic gunshot residues. Josh already introduced us, so I'm going to just add that Dr. Suzanne Bell, as Josh mentioned, cannot be here with us today, but I'll be presenting on her behalf. I'm going to be presenting and discussing her research on LCMS work. Dr. Luis Arroyo's presentation today will be focused on the electrochemistry application for gunshot residues, and I'll be presenting on the application of laser-induced breakdown spectroscopy, or LIBS. We are very proud of what we are presenting today, and these are the real stars. We have a very active research group in gunshot residues. For our gunshot residues research in particular, we have 5 undergrads, 4 PhD students, 1 visiting student, and 1 postdoc. So I'm going to introduce first our undergrads. From left to right in the bottom row, we have Emily Heller. She works primarily with SEM, EDS, and ICP-MS instrumentation. Zachary Andrews, he has been very helpful in sampling and also applications with LIBS. Emily Halpern, she works primarily with LCMS on gunshot residues. And then in the second row, now from right to left, we have Courtney Dassel, who works on electrochemistry detection, and Oriana Ovide, who works on sampling, LIBS, and color testing. Claudia Martinez Lopez joined our group as a postdoctoral scientist this past August. She graduated with a PhD from Florida International University. Corina Menking-Hogat is a PhD student in our forensic science program. She is the recipient of an NIJ STEM Graduate Fellowship for the development and validation of inorganic gunshot residue standards for the characterization of modern ammunition. For what we are going to be discussing today, Corina helped a lot in the development and validation of the LIBS methods for the detection of gunshot residues on hands and the SEM-EDS analysis. Courtney Vanderpyle is another PhD student in our forensic program. Her research primarily focuses on the application of LIBS for shooting distance determinations and reconstruction of firearm-related investigations. Colby Ott is a PhD student in our forensic program. His work primarily focuses on development and validation of screen printing electrodes for the electrochemical detection of inorganic and organic gunshot residues. Pedro Calderon is a master's student, he's a visiting student from the University of Costa Rica, and he is helping us with the modification of screen printing electrodes with nanoparticles for improvement of the detection of gunshot residues. William Finney is a PhD student in the Department of Chemistry at West Virginia University. He is also an NIJ STEM Graduate Fellowship. He just recently got the fellowship, and he will be starting on that on 2020. His work primarily is on the validation of LCMS protocols for the detection of gunshot residues. We are also very fortunate to have 2 excellent statisticians on board in our team. So we have James Curran. He's a professor and head of the Department of Statistics at the University of Auckland in New Zealand. James Curran is a well-known statistician with a particular expertise in the use of statistics for the solution of forensic problems. Stacy Culp is an assistant professor at the Department of Statistics in West Virginia University. She's been also very helpful in the whole process of the project, and she's also a committee member from one of our PhD students. Professor Kit Morris at West Virginia University and his students, James Hamilton and Kayla Crossman, have been just wonderful for helping us with all the collection of samples at the WVU Ballistics Laboratory. He is the official ranger for our indoor forensic laboratory room, and he has been just fantastic in helping us to sample every time that we request. He has been a fantastic support for us. I would like to also thank Greg Corio and Jerry Land at West Virginia University. They are acknowledged for their support and coordination of the sampling and outdoors shooting ranges, particularly helping us coordinate the sampling at the Scout Jamboree events in 2017 and the Worldwide Scout Jamboree in 2019. It was a great experience for us, not only because we were able to collect literally thousands of samples in a couple of days in that event, but also had the opportunity to meet students and participants from all over the world. So it was a very well-rounded experience for our students as well, and an opportunity to share with people from different levels, different areas of the world, the research that has been done at West Virginia University and also sponsored by NIJ. I would like to also thank other collaborators, Professor Ana Lorena Alvarado from the University of Costa Rica, our industry collaborators. I would like to especially thank Foothold Labs for the support in the electrochemistry, Sean McIntosh, also Applied Spectra, who had been very key in our support with the LIPS instrumentation. So I would like to thank Young Yu and his wonderful team. This is our first year for this grant, so we are coming up to our second year. And in this second year, we are going to be working more closely with forensic laboratories. In particular, we have the support from Sacramento Crime Lab, Chip Pollock, the Department of Forensic Science in Virginia, Doug DiGaetano, and from North Carolina State Crime Lab, David Freeling, who they are going to be participating later on in the next year in a small interlaboratory study for testing by SEM EDS gunshot residue particles that we are creating in-house as part of the project. And finally, I would like to thank also Paul Speaker from the West Virginia University Department of Finance, who is going to be helping us later on in the project to do some return on investment approximations to evaluate what will be the impact on incorporating the technology that we are proposing in forensic laboratories and at the crime scenes. So with that, again, I would like to thank everyone that contributed so far in the project. And we couldn't have done what we are presenting today with all your support. All right, so now the reason why we are here today, the webinar will be divided in 5 parts. First, we will be presenting a brief introduction to gunshot residues, and we're going to be describing our approach here at West Virginia University for detection of GSR. Then we're going to be describing the results for different applications, including LIPS, electrochemistry, and LCMS, and finally, some summary conclusions and future work. The learning objectives for this webinar are first, to understand challenges faced in the forensic analysis and interpretation of gunshot residues and how emerging technologies can provide viable solutions. Second, recognize the main capabilities and limitations of LIPS, electrochemistry, and LCMS for gunshot residue detection and their potential impact to the criminal justice. And finally, identify the value of using populations that simulates caseware samples for the validation and assessment of performance measures of qualitative data. So with that, I'm going to pass the microphone to Dr. Arroyo.
Good afternoon, everyone, and thank you. The first part that I'm going to give you here are some numbers. These are some statistics of firearm-related incidents in the United States in 2017. The numbers speak by themselves. Gun violence results in tens of thousands of deaths and injuries on an annual basis. The most common cases involving gun violence are homicides, suicides, kidnappings, and assaults. The detection of gunshot residues can provide key information in these investigations and can help to corroborate testimonies, especially when GSRs are detected in hands and clothing or any other target reached by the bullet. So where are these residues coming from? When a gun is fired, there are several compounds that are released from the primer. The initiator, the fuel, and the oxidant are responsible for the generation of lead, barium, and antimony, and therefore they are known as inorganic gunshot residues. Also, there are over 100 different compounds that can be produced during the deflagration of the propellant, including nitrocellulose, nitroglycerin, DPA, and ethyl centralite. These are known as organic gunshot residues. SEM-EDS is the gold standard for the detection of inorganic gunshot residues. Advantages of this method are its dual capability for identification of the spherical morphology of the microparticles and identification of its elemental composition. The ASTM method provides some criteria for the interpretation of inorganic gunshot residue. First, morphology is important, but since it varies greatly, it should not be considered as the only criteria. So once a potential particle is identified morphologically, the elemental composition is inspected for confirmation. For standard ammunition, there are 3 levels of confidence in the interpretation of the elemental profiles. The highest level of identification is called characteristic of inorganic gunshot residue, and it occurs when the 3 main markers are present: lead, barium, and antimony. On the other hand, when only 2 of these are present, the sample is considered consistent with inorganic gunshot residue. Finally, when only 1 marker element is present, the conclusion is reported as commonly associated with inorganic gunshot residue. Similar recommendations are available for non-standard or lead-free ammunition, although their characterization is less straightforward. In spite of its scientific validity, SEM-EDS has several challenges. First, the method is time-consuming, usually taking over 8 hours per sample. Second, the introduction of modern ammunitions brings some challenges for the method. Lead-free or non-toxic ammunition may have compositions with lighter elements requiring adjustments of contrast and other parameters in the automatic routines. And with the variety of elemental composition, standard markers are not as standard anymore. For instance, during our research, we have found several examples of standard ammunition that does not contain barium, and this is the case of this Tulamo. Also, some non-toxic ammunition, like the one shown here, does not have neat spherical morphology and only contains light elements that are prevalent in the environment, such as potassium, aluminum, and silicon. And these bring us to the next challenge, which is requiring an increased reliability in the analytical result. SEM-EDS is, in our opinion, not longer the solution for every type of ammunition. The literature has reported that GSR particles are not always spherical, and that some non-GSR particles may share similar shape or composition. And as a result, the community is looking for complementary methods for the detection of organic gunshot residues. As I mentioned before, there are over 100 different compounds associated with organic gunshot residues that has been highlighted in the literature. From these ones, there are about 20 that are not as common in the environment and therefore have been reported useful for GSR identification. Some of these are presented in this table. So the motivation of our study was to develop an approach that overcomes some of the main challenges of speed, preservation, accuracy, and interpretations. We propose to develop a practical, simpler, and faster approach for the simultaneous detection of both inorganic and organic gunshot residues. Our ultimate goal is to develop methods that can increase the reliability and efficiency, providing valuable data and a streamlined process with fewer errors and delays. So we propose to do that by building capacity using emerging methods that can increase not only the data quality, but most importantly, the usage of that data for increased impact. And of course, we want those methods to be cost-effective so they can be accessible, easy to maintain, and practical, and fast so we can provide rapid feedback to the users. So what we propose is first, the development of methods that are compatible with universal collection methods. so we don't have to incorporate changes to current practice. And second, use methods that are fast and orthogonal so we can obtain complementary information of inorganic and organic gunshot residues, like the case in LIPS and electrochemistry. We are not the only group that has reported the use of LIPS or electrochemistry for GSR analysis. But the novelty of our approach is that we are the first ones in developing the methods directly on an SEM carbon stubs, combining both technologies, validating them with a large population of authentic samples, and applying a statistical interpretation of the data. Also, as the methods are almost non-destructive, we can still use confirmatory methods if needed. So why did we choose LIPS and electrochemical sensors? So just to give you a glimpse, in the case of LIPS utilizes a pulse laser for direct qualitative and quantitative information. It's a very rapid chemical analysis technique requiring less than a minute. There's no sample preparation involved and provides a minimal destruction at the surface material. And most importantly, the simultaneous multi-element detection in the low parts per million range. In the case of electrochemistry, we're going to use an electrical stimulation to induce redox reactions at the surface of the electrode so we can obtain simultaneously both inorganic and organic information. It is very rapid response, low cost, and offer good sensitivity and selectivity. And as we're going to learn later on, is portable and non-destructive. But first, we're going to study later with the fast GSR analysis for LIPS, and I'm going to pass my mic to Dr. Trejas.
Thank you, Liz. So let's see how LIPS works. In a LIPS system, the sample doesn't require any sample preparation. So we can place directly the SEM stop if we are collecting samples from hands or the clothing, and can be placed directly into the ablation chamber as is shown here in the picture below. Then a pulse laser beam of just a few microns in diameter is fired into the sample, and the interaction of the laser with the sample produces a temporal microplasma containing information from excited ions and atoms. When these excited species come back to the ground state, they emit light at characteristic wavelengths that are captured and detected by a spectrograph. We can measure a spectra for these species from UV to infrared regions, being able to literally detect almost every element in the periodic table in just a few seconds. The first application that I'm going to briefly describe today is the use of LIPS for shooting distance estimations. As you all know, the estimation of contact, close range, or long distance shootings can be critical in the reconstruction of events and is normally conducted by colorimetric tests in the laboratory. We propose to modernize current methods by using LIPS for fast chemical mapping. With LIPS, the laser beam can be quickly scanned as we move away from the bullet entrance hole, while acquiring in real time the chemical composition of multiple inorganic gunshot residue markers. In this example, we can see how lead and barium signals were decreasing as we move away the laser from the entrance bullet hole. So we can use this spectral information to generate 3D maps of the distribution of inorganic gunshot residues around the crater, as shown here in the diagram in the bottom, where we can see the different distributions for contact 6 inches, 12 inches, 24 inches, and 36 inches away for, in this particular case, for lead. Advantages of this method is that provides superior sensitivity and selectivity that color test, and also increase the objectivity in the estimation of the shooting distance. For example, LIPS is several orders of magnitude more sensitive than the color test sodium rhodisonate. In this example, I'm presenting, for example, the limit of detection for LIPS for lead was 70 nanograms, while the equivalent test for the sodium rhodisonate in color tests can only arrive to 7,000 nanograms. And likewise, for leaves, we can reach detection limits in the order of 0.2 nanograms, while with the color testing of sodium rhodisonate, when that pink color is generated before the creation of the purple for lead, barium can detect it only at about 5,000 nanograms. In addition, color tests become more challenging with dark and bloody backgrounds, which are pretty common in casework. We did observe, for example, that when we use dark colors or pattern clothing, then the observations of the physical features around the crater become less obvious, and we have to use indirect color testing as well. We also observe, for example, that some blue and black dyes interfere with the Grice test, while leaves clearly identifies lead, barium, and antimony with no interference from the fabrics, as observed here in this spectra on the bottom, where you can see the signal for barium in red, and then in the insert of that spectra, you can see that there is no signal coming from the different fabrics that we tested for that barium signal. The chemical information was used to train linear discriminant models, and we use unseen data that we call blind unknown data because it's blind to the analyst. So they don't know what is the distance that we have been shooting. We provide the samples, they do the analysis, and they use the calibration data to test how well these models can predict a shooting distance. So we keep it blind to the process until they submit the results, and then we can evaluate how well the methods perform. So in this particular case, in dark color samples, the visual inspection was not helpful. Color tests only led to the right distance determination 67% of the times, while LIBS was able to correctly estimate shooting distances in all the unknown samples. Similar results were observed for blood stain samples, where a significant improvement was observed when using LIBS as compared to color testing. So we improved from visual examination 50% to color tests 70% to the use of LIBS for 100% correct identification of the distance. We published this research recently in Spectrochemica Acta B, and a second publication is coming up soon. So we are spending the rest of the talk describing our second application, which is the detection of gunshot residues from the skin of hands. To validate our methods, we designed, with aid of our statisticians, a data set composed of over 300 from shooters after firing standard and non-toxic ammunition and after doing some activity, and from non-shooters, including low-risk and high-risk background populations. So far, we have almost doubled our sample size expectations. So in the following slides, we will be describing the results for samples from 320 individuals collected less than 3 hours after shooting. We collected 4 samples per individual, left hand, right hand, palm, and back, respectively. So that's for those 300 samples, that's over 1,000 samples that we collected and analyzed. We also sampled 300 individuals from a low-risk population of non-shooters. And we use this data to estimate how many times that we have a sample from a shooter we correctly identify the presence of gunshot residue. We call these ones true positives. And how many times we correctly identify a non-shooter sample as a negative result. We call those true negatives. And we also use these validation sets of known samples to determine how many times we get false negatives and false positive results. We use 4 different approaches. The first one is more exploratory to determine the positive and negative threshold based on the confidence interval of signal-to-noise ratios from the background populations. We also use 3 machine learning algorithms to distinguish between 2 groups. Here, we're going to refer to these groups as non-shooters, and those are the samples from background population. And then the second group, we're going to call it the shooter group, and those are samples from individuals in the vicinity of a firing. For instance, I selected few samples here to give this example just for a better visualization purpose. So we start with our background population, highlighted here in sky blue. We calculate our threshold as the mean of the skin background signal plus 3 times the standard deviation. So that's considered our threshold. And then a true negative will be a skin sample that is present below that threshold. A false positive will be a non-shooter skin background with elements present above that threshold, like in this example that I provided here, represented in red, in which we detected antimony and barium above that threshold for one of the non-shooter samples. Then a true positive is a shooter sample in which we detected elements characteristic or consistent with inorganic gunshot residues and are above that threshold, represented here in green. In contrast, a false negative will be a shooter sample with no detectable GSR markers. 3 classifier supervised methods were used in this study to evaluate their ability to predict class membership: logistic regression, naive Bayes, and neural networks. K-fold cross-validation was repeated several times. This means that approximately half of our data was used for validation and the other half for testing. The training and testing data sets are selected random. Therefore, to avoid the results being driven by a single random selection, the procedure was repeated several times and the average performance was reported. The results of the algorithms provide confusion matrices. In these confusion matrices, we can determine how many times a shooter sample was confused with a background sample and vice versa. And these were used to calculate the performance rates. The figure at right represents a simple neural network consisting of 7 input variables and 3 nodes with 1 hidden layer. An advantage of classifier methods is the capability to learn patterns derived from large populations and provide probabilistic outputs that can be later used to support the interpretation of the evidence. So the first method, LIPS method that we developed, consisted in accumulating the spectral data from a rapid ablation of a line of only 100 micron in diameter by 7 millimeters directly on the carbon stop. So we were using only 0.6% of the total area of the stop. So here is the carbon stop after ablation on the left and the respective SEM imaging showing the minimal damage produced after ablation on the right. The result of this ablation is a rich spectrum like the one that you can see here, in which we can simultaneously detect for a sample several emission lines per element, therefore providing better confidence in the results. In this particular example, I'm zooming in to demonstrate that we use at least 2 emission lines per element, 2 for antimony, 2 for lead, and 2 for barium, although we can monitor a lot more than that per element, and that's one of the advantages of LIPS, because that provides better confirmatory or confidence in our results for the presence of an element. This preliminary work was published in the Journal of Forensic Chemistry, and a second publication is coming up very soon. So we decided to push further the capabilities of LIPS. So we went ahead and improved the method that we were developing using the line method, but now we were collecting the data from only 2 laser shots in an area of only 100 micron in diameter. So we fired twice and we collect the data. In doing that, we now gain the ability to see if we are simultaneously detecting characteristic elements from a small location, as observed here in this example for the area highlighted as 13, in which we can see in that particular location simultaneously the presence of lead, barium, and antimony. And although we cannot guarantee, like in SEM, that the ablation is coming from a single particle, it does provide valuable spatial information that increase the confidence in the results because we are identifying the inorganic gunshot residues markers from a very small area. We repeat this process 25 times per sample, so we can collect 25 spectra per stop. And again, we can collect these 25 replicates in just a minute and a half using only 0.2% of the area of the carbon stop, leaving the sample almost unaltered. So we use the 320 shooters and 300 background skin individual samples to validate this method using different ammunition and collected from indoor and outdoor shooting ranges. These box plots show the distribution of lead, barium, and antimony on background and shooter populations. And as I mentioned earlier, we use that background data, background population data, to set up our positive and negative thresholds. From this population, we can then estimate the number of false positives, false negatives, the true negatives, and true positives. And with that information, we can estimate the accuracy of the method to differentiate between a shooter or non-shooter, or between the presence or absence of gunshot residues, to be more exact. So from this population, the accuracy observed with leaves range from a little over 79% to 98%, depending on the classification criteria, which is pretty good for a screening method, particularly considering the advantages that we discussed before. I want to note, however, that when we collected samples at the Scout or Jamboree, they were firing both standard and non-toxic ammunition. So this set is very likely to include a mixture of standard and mixed formulations, which can affect the ability of the models to predict positive samples so far. So this represents a worst case scenario. We are working on generating the non-toxic population. We have already a pretty good number of standard population, and when we have the two of them, we can combine mixtures of that population to get a better estimation of the error rates in these cases in which we can have mixtures of standard and lead-free ammunition. So to give an example how that can improve the accuracy, when we use only the population from standard ammunition, here in this case we have 100 shooters and 100 non-shooters for about 500 samples in total. The specificity, sensitivity, and accuracy are significantly improved, now ranging from over 87 to 99% accuracy. Not bad at all for a screening method. So in conclusion, LIBS is a promising analytical tool for the fast detection of inorganic gunshot residues. It can be used for shooting distance estimation. In the advantages are that it's faster and non-invasive. It provides also superior selectivity, sensitivity, accuracy, and objectivity that current color methods. For the application of LIBS for residues from hands, the method provides high accuracy and distinction between shooters and background populations. And one of the great advantages is the speed and ease of analysis. We don't require any sample preparation. It only requires about 2 minutes per sample. So we can do a very simple case of 4 samples and the controls in less than 15 minutes per case. And with that, I'm going to pass again the microphone to Dr. Arroyo, who is going to be discussing the forensic electrochemistry data.
Well, thank you, Tatiana. So we are going to describe the fundamentals of electrochemistry in very simple terms. Electrochemistry refers to a study of chemical changes as a result of applied electricity that we call potential. Of interest in this study are oxidation reduction reactions involving the transfer of electrons between species, as demonstrated here by the reduction of lead ion to metal and oxidation back to the ionic form. This movement of electrons or charge is termed the current. This current is then used to provide a relationship between the current flowing and the amount of analyte in solution. Electrochemistry is a mature analytical technique that has proven to be a versatile platform for many types of analysis. The demand of more efficient analytical techniques leads us to practical solutions where electrochemistry plays a critical role. In this slide, I'm presenting several relevant fields of study that have benefit for using electrochemistry to solve particular problems. Electrochemistry offers a variety of advantages, including excellent detection limits, a wide dynamic range, is very rapid, and requires very small amounts of sample, is relatively inexpensive, and we're going to see later the portability feature. In most electrochemical measurements, there are four main components necessary for analysis. The first is the supporting electrolyte. This is normally a buffer containing a high concentration of ionic species that are ideally unreactive to the analyte. This high concentration of ions in solution lowers the resistivity inside of the analysis cell, allowing the current to flow. The second is the working electrode. This is where the redox process occurs. Potential is applied to this electrode to facilitate the electrochemical change. This electrode can be made of many different materials, including carbon, silver, gold, and others. Modifications of the working electrode are also commonly performed depending on the application. The third is the counter or auxiliary electrode. This electrode is made of an inert metal, most often platinum, and completes the current loop, allowing the current to flow through the cell to the working electrode. Last is the reference electrode, which is important because it provides a constant potential from which the potential applied to the cell is compared against. The most common of this one is silver and silver chloride. As you can see from this cell, this is a bulky scenario. So therefore, in order to make this technique portable and attractive for future users, we use screen-printed carbon electrodes, or SPCEs. SPCEs incorporate the three electrodes discussed previously into a single unit that is smaller and easier to manipulate. Also, these electrodes are inexpensive and simple to manufacture, which allows them to be a disposable testing platform, eliminating the need for cleaning the electrodes between every sample. The simplicity of the fabrication also allows for good reproducibility between batches of electrodes. And lastly, the compact design and the proximity of the electrodes allows for small sample sizes to be analyzed as opposed to larger volumes, meaning easier and more realistic sampling for GSR analysis. As I mentioned, the manufacture of these electrodes is very simple and follows a similar process as those that we use for screen printed t-shirts. Using various different paste solutions, the layers are deposited starting with the creation of the silver tracks onto a plastic substrate. For this process, different mesh screens are used to define the area to apply the paste and then is let it to cure. A carbon paste is then used to define the working electrode in the center and the counter electrode. A silver paste containing silver chloride is then used to define the pseudo-reference electrode. Then the entire system is covered with an isolating non-conductive paste to isolate and define the electrode areas. The electrodes that we used in this study were these carbon-based electrodes and are commercially available via different vendors. So let's see what we did. The electrochemical method is straightforward. It starts with the addition of an extraction buffer into the surface of the carbon stop, as is highlighted on the left portion of this figure. This fraction is collected and placed in a centrifuge tube for later use. Next, acetonitril is used as a quick wash of a portion of the surface, and this aliquot is dried down with nitrogen and reconstituted in the original buffer extract that we previously collected. This aliquot is transferred to the electrode for analysis, as is observed here on the right-hand side of the figure. What is important to mention is that this process takes approximately less than 3 minutes. This is an example of a real sample from a shooter containing lead, copper, and nitroglycerin. Each one of these compounds show peaks at their characteristic potentials. Like in LIPS, we also study the distribution of the data to establish critical thresholds. As can be seen from this figure, background levels from non-shooters are significantly lower than those observed from shooters. In this example, we can observe lead, copper, and nitroglycerin for your reference. For the validation study, we analyzed the same 620 samples described by LIPS. What is important to note is that we did electrochemistry on the same exact sample after LIPS analysis, and yet we were able to identify both inorganic and organic gunshot residues. The accuracy, as you see at the bottom of this table, for the case of electrochemistry itself, ranged from over 77 to 99% in accuracy. What is even more encouraging is that, as we expected, when combining the LIPS and electrochemical data together, the performance of classification improved regardless of the statistical model, with accuracy ranging from 95 to 98%. And remember, detection of both inorganic and organic gunshot residue is possible using both methods in less than 5 minutes per sample. And moreover, we have been able to detect GSR by SEM-EDS on the same sample after LIPS and electrochemistry is performed. Although this technique fits for purpose, we are still finding better ways of using electrochemical sensors. So we are enhancing the electrochemical signal with nanoparticles. The use of nanoparticles increase the surface area of the electrode and therefore improves the current response. 3 different methods were used in our study. The first one utilizes the bare carbon electrode without any modification and using the square wave voltammetry. Here, the sample is deposited directly into the electrode surface for measurement. The other 2 methods use gold nanoparticles and differential pulse as measuring technique. The first nanoparticle method is also a direct deposit of the sample at the surface, while the third one involves, as you see on the left, the immersion of the electrode in an electrochemical cell as shown on the left. And here is where the gold nanoparticles are crucial. The table on the right shows the limits of detection for the suite of elements and compounds that we have measured so far. As you can observe, both gold nanoparticle methods increase the sensitivity of the method significantly when compared with the bare carbon method. The figure on the left presents the data in a graph format, where the y-axis presents the limits of detection in parts per million. Therefore, the lower the bars, the more sensitive the measured species. So the general conclusions for both LIPS and electrochemistry is that the proposed screening methods are a promising approach to modernize GSR detection and provide fast decision-making in firearm-related investigations. Some of the advantages of LIPS and electrochemical methods include the following: the speed and ease of analysis requiring between 1 to 3 minutes per sample or 15 to 20 minutes per case when we combine both technologies. High specificity and sensitivity is gained when we also combine both capabilities. And there is a lot of potential for on-site detection. Machine learning algorithms offer a superior prediction model in this analysis, and ongoing efforts, including the creation of a larger data set that includes a variety of ammunitions and populations to serve as a basis for probabilistic interpretation of GSR evidence, is expected. So with that, we're going to continue with the part 4 of this webinar that includes the single confirmatory protocol by LCM-SMS. I'm going to pass the microphone to Dr. Trejos.
Thank you, Luis. So last but not least, I'll be presenting Dr. Bell's group LCMS work. She is currently retired, but continues as the chair of her PhD student, Bill Finney, who has done his work and deserves all this credit. Since her retirement, I'm serving as co-chair for Bill's PhD, and I'm honored to share with you this research. As we mentioned earlier, there has been an increased interest in detecting organic gunshot residues to enhance the reliability of gunshot residue evidence. And we are not the only group that has developed LCMS detection methods for these purposes. But the novelty of our approach is the detection from the same sample using sequential extraction for dual detection of inorganic and organic gunshot residues, and detection and confirmation in a single instrument that is accessible to most crime laboratories nowadays. We have tried different polymers for collection, but now we are pretty much set on the tape adhesive and the universal SEM carbon stops. So this slide shows you the materials that we use. We have tested both the TESA tag that is in the top image over there and the SEM carbon tape adhesive. Both work very well for the extraction and sampling. The extraction that we use for organic gunshot residue is typical. It is aligned with what most groups have reported in the literature. The inorganics are done with a microbulk extraction. This is essentially an acid digestion done directly in a microcentrifuge tube. Digestion is very simple. You add the acids, heat for 15 minutes, draw an aliquot, and mix with a complex agent. The way we detect the inorganics is by forming a guest-host complex. We have first to solubilize the inorganics like lead, barium, and antimony, and once in ionic form, they form a complex with the host, and the complex is strong enough to survive electrospray. Once the solution is made, we do chromatography, and then the complex is ionized. We look at the precursor ion on the first quadruple, and then you fragment down to the bare metal cation, as you use isotope abundances for verification of the species. So you look for the complex, select the MRM transitions, and look at the isotopic ratios to confirm the presence of the elements. So this gave you an idea of the inorganic, how the inorganic extraction works. At this point, the organics are done. The polymer is dried down. So this is sitting down in the bottom of the centrifuge tube. We add the acids, heat, so we have the ions we need in solution, and you add the complex agent. We are using crown eaters and tartaric acid as the ligands. It does not form only one complex agent, however. We get lots of complex here, so just we pick the ones that provides the best intensity and performance. We fragment down to the bare metal and identify them based on their isotopic composition. So this is one of the crown eaters. Crown eaters form complex by association. It's a non-covalent association, so cations like calcium fit very well and form very strong complexes. The one I'm showing here is for lead. The bigger cations tend to sit on top when you model them, and they form like a sandwich structure. But in the case of antimony, the complex is not effective. Antimony is our problem child, so we have used instead tartaric acid that works very well for antimony, and we found that in the environmental science literature. Anyway, this is how we use these complexes, and they survive very well the electrospray, so we can do a lot with these in LCMS. Dr. Bell and Bill published earlier this year the method on FSI that provides the proof of concept. We have further optimized and validated the method and currently working on a second publication. Here is an example of what you see with lead and barium. So you can see the metals form multiple complexes. The typical most intense one is the sandwich complex that I mentioned before. And you can see that in those complexes, you can also observe the natural isotopic pattern coming from lead or barium respectively. This is what you are looking for when you screen, and you can use also exact mass calculators to corroborate. So to give you an example of the identification criteria that we use for barium, you look for the isotopes. So barium has different isotopes with different natural abundances. You get the precursor ion, fragment it down to the metal, and you have to see the isotopic ratio relative to the biggest isotope. We calculated not only the mean of that isotopic ratio, but also the experimental confidence interval so that we can be confident in the identification of those species. The total ion chromatogram that you see here is the sum of all transitions in red, from the sandwich complex ion down to the bare cation. So there you look at barium-138, for example, that is the most abundant isotope, and to identify that, we have to look the relative abundances respective to other ions. So we look at barium-137 at 19.2 abundance plus the confidence interval, and then the respective abundances for barium-136, and so on. So that's how you do the identification. This is a similar trace for lead, TIC on the left, the isotopic signatures on the right, and we can see that after one shot, lead is recovered from the skin. The signal to noises here are based on skin background signals, similar of what I discussed before for lips and electrochemistry. You can observe the MRM transitions and you can see that they are way above the background of skin threshold, so this is unambiguous that you can detect lead. You can also confirm here the relative isotopic abundances. Here we can see column chromatography, showing that we can complex and run on the same column all metal Hughes complexes, in this case for lead, barium, and antimony. As I mentioned earlier, antimony is one of our difficult elements. It is difficult to detect by lips, but we can do it, but it's not the most sensitive. It's difficult by electrochemistry, but it's doable. And it's also difficult by LCMS, but we have found a way to get around it as well. So initially, antimony was not forming complex with the crown ether, but the taric acid worked great, where you can now see the isotopic pattern for antimony in the negative mode. So it works fine, but now we have to use two complexing agents, one for lead and barium, the crown ethers, and one for antimony. We have tried alternative crown ethers, such as this example, the dibenzo crown ether, and which you can see the structure here, as this one provides improvement in the chromatography. We can see again here the fragmentation and isotopic ratios, which in this case, we were using high resolution just to confirm the presence of the species. This example shows high-resolution mass spectrometry for the fragmentation identification down to the bare metal for lead with the crown ether, the dibenzo crown ether. For organic gunshot residue, we have focused on the top 6 major markers that have been consistently reported in the literature: ethyl centralite, methyl centralite, DPA, and the NDPA family. Since our last publication, we did some additional optimization and improved detection limits. We spent a lot of time working on identification criteria, making sure we have good confirmation by retention time, ion ratios falling within the validation rate, good linearity, and good reproducibility over time. In our preliminary study, we collected gunshot residues on hands after firing pistol and revolver after 1, 2, or 3 shots. We consistently identified ethyl centralite and lead in the samples, so this is the same sample, and we are picking up both organic and inorganics in multiple samples. This is an example from another set that we ran for 20 authentic samples from shooters. Here is an example of one of them. We were able to see every compound except the methyl centralite, which we suspect is not in the Winchester ammunition that we use for this particular set. But you can see the ethyl centralite, the phenylamine family, and the other compounds. So in conclusion, LCMS provides orthogonal information in gunshot residues analysis with advantages of using technology that is available in most crime laboratories. It's capable of detecting in a single shot skin sample several organic and inorganic components. And right now we are working on creating more samples for the population study and validate this methodology. And this brings us to the last section of the presentation. So let's compare for a moment the analytical performance of the methods. SEM-EDS can detect anything above 0.1%. That's about 1,000 ppm, but it has the advantage of doing single micron particle analysis. It cannot, however, detect organics. LIBS has superior detection capabilities, typically 1 or 2 orders of magnitude better than SEM, but spatial resolution is limited to 100 micron area. There are very few elements in the periodic table, however, that we cannot analyze simultaneously by LIBS, so it is very versatile. Electrochemistry and LCMS can both detect inorganic and organic gunshot residue. Electrochemistry can do it simultaneously in a single run, with limits of detection in the ppb range for both the inorganic and the organics. Electrochemistry can detect main inorganics with the exception of barium. Barium is problematic in electrochemistry, but is the best emission element for LIBS, and that's why they complement each other so well. In electrochemistry, we have focused so far in detecting 4 major organic compounds, so we are reporting only those here, but we are expanding our suite of organic compounds as we speak. LCMS has inferior detection limit than electrochemistry for the inorganics, but it has better detection capabilities for the inorganics in the low, for the organics in the low ppb range. It also has, of course, better confirmation power. I also want to note that regardless of their difference in detection capability, all these 4 methodologies were able to detect the markers on real samples, so they fit for purpose. Let's now explore other capabilities. Electrochemistry and LCMS provide dual detection of the inorganic and the organic gunshot residues. LIBS and electrochemistry provide ultra-fast alternative methods for the detection of inorganic and organic gunshot residues when combined, with minimal sample preparation and minimal damage to the sample. In terms of time of analysis, electrochemistry and LIBS provide unprecedented capabilities. For instance, just to give you an example, we were able to analyze thousands of samples that we collected in the summer from the Jamboree only in just 4 days with both methods. We are, in comparison, still analyzing samples from the summer by SEM-EDS. SEM-EDS is a lot slower and definitely our bottleneck. Electrochemistry and LIBS have the capability also for laboratory and on-site analysis. And why is this important? I'm going to give just an example. For instance, there are currently about 100 cities in the United States that use acoustic systems to detect the sounds of gunshots. So law enforcement are effectively arriving at the scene in just few minutes. Unfortunately, there are not technology available that can match the speed for detection of gunshot residues. So law enforcement had to wait weeks to months to get a pretrial result, and the electrochemistry and LIBS have really a potential to change that, the way we do that type of investigations. LCMS offers an appealing confirmatory method of organic and inorganic gunshot residues with low limits of detection and a relatively fast protocol. So I think the take-home message that we want to stress today is that together, these methods provide means to modernize the analysis and interpretation of gunshot residues and help overcome challenges of modern ammunition and GSR investigations. In our opinion, we have to evolve and rethink how we can provide smarter solutions. Can we, for example, triage with fast screening methods? Can we expand our services and reduce response times? Can we incorporate more comprehensive analytical protocols instead of trying to find one method that fits for all case types? I think we can. We can provide simpler, modern, affordable, rapid, transformative, effective, unreliable solutions. So in terms of future work, we're going to be analyzing larger population studies so that we can provide fully statistical interpretation alternatives. We are also characterizing modern ammunition by different methods, and we are going to be starting next year a cross-validation of methods and an interlaboratory collaboration. So if any of you are interested in finding a little bit more about the interlab studies, please feel free to reach out to us. And finally, we will be planning for technology transfer so that we can objectively evaluate how the incorporation of these type of methods and protocols can benefit the operation in forensic laboratories and at the crime scene. And with that, we conclude the webinar, and now we are open to questions. Thank you.
All right, thank you so much, Dr. Trejos and Dr. Arroyo. We are going to move into our Q&A. We do have a few questions that have come in, but before we jump into that, I do want to make mention of the email addresses that our presenters have both put up there on the screen. So do make sure that you take those down before you leave today, just in case you have any follow-up questions. Also, we are providing a PDF version of today's slide deck. Once we are finished with the webinar for today, it will be located back on the main page, so you will be able to download that before you leave today. All right, so the first question came in for you, Dr. Trejos, while you were presenting about midway through, asking what was the value of K in K-fold validations, and how many data points were used besides the 50% information that was given?
Okay. So it varies by the type of method that we were using. So in general terms, for example, for the neural networks, we use the K-fold option, divided the data in 3 subsets, 60% of the data for training, 20% for validation, and 20% for testing. So we use a K-fold option for 5 times. So we accomplish this by processing the data 5 times with different combinations of the data sets to ensure the algorithm was being properly trained. In terms of data points, we had about 600 samples. So we had 300 backgrounds. We collect 2 samples per background per individual. So we have left and right hand, so that's 600 data points. And for the shooter samples, we had 320 times 4, so over 1,000 samples from 320 individuals.
Okay, next question can go to either one of you in regards to the overall study. How close were the non-shooters to the shooters?
So this is a good question. We haven't done non-shooters in the proximity of a shooters. We haven't done that yet. So the background samples that we describe are all what we call low-risk population. So these are individuals that have not been in the vicinity of a shooting and individuals that have reported themselves that they don't have like hobbies like shooting, or that they don't have, for example, any police work, or they don't manipulate mechanical work that could produce some contamination. So we are proposing to analyze 2 big populations. One is the low risk, the other one is the high risk. Right now, we only have analyzed the low risk background samples, and those are individuals that were not even close to the shooting event. So we did it in 2 different locations, or more than locations, but they were not near the shooting range where we were sampling the shooter samples.
All right, next question we have came in from Shirley asking, how do you deal with the losing of simultaneous detection when using EC?
Can you reformulate the question? I'm sorry.
How do you deal with the losing of simultaneous detection, the same particle, when using EC?
Okay, so I'm gonna answer that, and then I'll pass it to Dr. Arroyo. So in the case of electrochemistry, we only use a partial wash of the stop. So only about a quarter portion of the SEM stop is used for the electrochemistry work. So we leave the rest untouched for SEM analysis. But even then, also when we do the electrochemistry is non-destructive. So once we have done the analysis, we have also analyzed the electrode after analysis. One is dried down. The particles of gunshot residue remain on the surface of the electrode, so you can put those directly on the SEM as well. So that's why we said it's non-destructive, because either we have particles remaining in the carbon stop, or the ones that we're taking away for the electrochemistry remain dried in the electrode, and that is very easy to observe on the SEM because they have a carbon background or a gold background, and they are non-conductive. So we don't have any charging effects. So that's what we consider that a non-destructive nature.
And also, just to follow up on that, the extract aspect of ACN is minimum. We use basically 50 microliters of extraction. So we just cover a little bit of the carbon stop just to perform the extraction of the organics. So that's just to end up with that little amount of exposure for the carbon stop.
All right. Next question that came in is asking, regarding your study, are there any thoughts of doing a study on multiple shots fired versus just the single shot?
Yes, that's a great question. We have done that so far with LCMS. We have tried 1, 2, and 3 shots as well as 5, and we didn't find like significant difference. Sometimes you get similar results, sometimes you have less results. So far in the experiments that we have conducted, it doesn't seem to increase in one direction or the other when you have 1 versus 3 shots. We have also done similar studies with the leaves at the very beginning of the study, and we really didn't find that we get like X number of or significant larger number of particles when we use 1 shot versus multiple shots. We do, however, when we do the collection for the shooter samples, we have a specific protocol in which the individual will wash their hands very thoroughly and apply alcohol between shots, so that we do, for example, 3 shots or 5 shots, collect that from a sample. If the same person is going to be the shooting, then it goes through a thorough washing process before collecting the next sample.
All right. Next question we have that came in asking, what was the difference when collecting GSR from hands at 3 minutes versus 3 hours or possibly longer?
So we have 2 populations. One is the shooters directly from activity, directly after shooting, and we consider that directly anything from immediately after versus 3 hours. We haven't done the study in how different is under control conditions at time 0, an hour, 2 hours, or 3 hours. In general, that whole population that we have presented so far is anything from time 0 to 3 hours, a combination of those. Later on, we are proposing as well one population in which we're going to be controlling activity and time. So hopefully we should be able to answer that in a couple of months once we have completed that population, but we don't know yet. We haven't done that activity or post-activity population yet.
Okay. Nicole's asking, what LIBS instrument do you use and how much does it generally cost?
So we are using a LIBS system from Applied Spectra. There are different configurations for LIBS systems. The one that we are using is an UV laser, so 266 nanometers. And in terms of price in general, is in the range of the 100,000. But it really depends on configurations. But just to give you an idea, the electrochemistry unit are less than $10,000. LIBS is about 100 or so. It depends on the configuration, so you can kind of compare that the technology is relatively cheaper, especially in the case of electrochemistry and even for LEAPS when we compare to LEAPS to SEM EDS, for example.
Okay. Next question comes in asking what type of weapon was used to place the gunpowder into the air?
So we use, let me see if I can go back to that. I don't know if I have I think I have ammunition here, but we have used many different types of pistols and revolvers, and we have used different type of ammunition, different calibers. We haven't tried yet rifles. All it has been handguns like pistols and revolvers. Let me see if I can find quickly that slide to show you more details. Yeah, we have only here. We don't have more detail in here, but in this particular set, we have pistols, we have 9mm and 22. We have also used revolvers. We have a lot more data than the one that presented here. The one we are presenting is data that we have on the same exact sample, LEAPS and electrochemistry or SEM data. So we have used a variety of pistols, a variety of revolvers with different calibers, different type of ammunition so far. Is there more questions, Josh?
Oh, yes, I apologize. I was on mute. Just for everyone's reference, again, you can find the PDF version of today's slides back on the main webinar page where you came into the event. So make sure you do download that before you leave today. The next question is asking, is there a control standard for the LCMS?
So that's a good question. So we so far are using different quality control standards. We are using the pure standards and mixtures for the organics. We also use pure standards for the inorganics. We also use something that I didn't have time to go over today, but hopefully the AFS Academy meeting, that's what we're planning to present in one of our presentations. That's actually Corina's, one of my PhD students' work, and that's the fellowship that she got from the NIJ. She has developed, in collaboration with the Sacramento Crime Laboratory, a standard gunshot residue particles that are inorganic in nature, so they come primarily from the primer. And she has been doing a thorough characterization of gunshot residue standards coming from non-toxic and also standard ammunition. And those have been thoroughly characterized by ICP-MS, SEM, EDS, LEAPS, and LCMS. And we have evaluated the stability of those particles over time so that eventually that could be a great advantage of having a standard that we can use for cross-validation of the method. So we have some of those in-house standards, and we have been using those with known composition and known number of particles per volume to validate the inorganic portion of the LCMS. For the organic portion of the LCMS, what we have used are the NEAT standard solutions and mixtures, and then of course using authentic samples to corroborate. So when we have an LCMS result for organic, we corroborate that with electrochemistry and vice versa. But unfortunately, we don't have knowledge of an existing gunshot residue standard that has the particle shape and morphology for the organic portion. We are working on that, on developing our own for the inorganic so far. But this is a very important issue in general, in GSR standards are lacking. So that's something that we are trying to develop and work to provide a solution also for the community.
All right. Next question came in asking, are you aware of any forensic science labs that have incorporated these newer GSR testing methods to complement the SEM EDS analysis, such as in casework?
No, so this is a pretty new study. As I mentioned, mentioned earlier, one of the things that we are trying to elaborate in our second year operations, so that we can start testing pilot testings for our is that because of the low cost of this instrumentation and the high versatility, in particular because we can use portable instrumentation and in-lab instrumentation, we expect or anticipate that it can be easily adopted at the crime scene at the laboratory. And that's something that will be an important role playing in this project. It's actually a formal study with the finance department here. He's the manager or the one that directs the Foresight project. So he knows very well all the numbers and statistics and in the area of crime laboratories and crime scenes. So he's going to be absolutely helpful in the terms at the end of this project, evaluating and helping us conduct a formal assessment of the advantages and return of investment should these methods will be fully incorporated at the crime scene or as a triage for screening at the laboratory. So that is in the works, but I don't have the answer yet. I know there are a couple of laboratories that are collaborating with us that are very interested in using their sites as pilot testing for the incorporation of this technology. So we're looking forward for that, but that's going to be happening next year.
Okay. The last question we have so far.
Sorry,
go ahead, Luis.
Josh. Yeah, no, I just want to mention that we also established a direct collaboration with an industry partner. So he has, for example, a portable unit that is also important to demonstrate the transition between what we have developed in the lab and also on an actual portable miniaturized unit. So I think that it will also contribute to the dissemination and the incorporation of this technology in the future in the crime labs. So just to add a little bit more info on that.
All right, thank you both. So the last question we have that came in right now is asking, does LIBS have the capability to detect GSR even after thorough hand washing?
So that's part of the activity population that I mentioned before that we haven't studied yet. So we don't have that answer yet. So we will have to evaluate that. But that's one of the issues with gunshot residue in general, right? Persistence is something that we have to be aware of. In washing the hands usually removes the majority of gunshot residues particles. So that's something we will be able to answer in more detail once we have that population study that we are planning with post-activity after firing.
All right. We will give everyone just another minute or two to have any last questions before we close out for today's event. Again, you will see Dr. Trejos and Dr. Arroyo's email address is up there on the screen now. You can also download the PDF version of today's presentation slides. It will be back on the main webinar page. Also, we are recording today's event as we do with all of our events. So we will convert that into our archival version that you will be able to reference back at any time or pass along to any colleagues that might have missed today's live event. So we do not have any questions coming in right now. So with that, we'll go ahead and wrap things up for today. But before we do, I would like to hand the microphone back over to Dr. Trejos and Dr. Arroyo just for any closing statements.
Well, first of all, I want to thank everyone who took the time to listen to the webinar. I hope you found it useful or informative. If you have any questions, please feel free to reach out to any of us by email. Or our website is the phone information as well. So please feel free to reach out if you have any questions or you want any further information. And thank you again to RTI and Josh in particular as well for all the support in running this, moderating this seminar.
Mm-hmm. And also thank you again for your time and Josh for your services there. And if there is any remaining questions, feel free to email us or call us if you want. And it's been a pleasure. So thank you.
All right, thank you both so much. Again, with that, we're going to go ahead and close out today's event. Obviously, we would like to thank our subject matter experts, Dr. Trejos, Dr. Arroyo, and then also Dr. Bell, who could not join us today. Thank you all for your countless hours of research and dedication that you've put into your field. Also, we would like to thank all the attendees for joining us today. Obviously, these webinars are just not possible without your attendance and support, so thank you for taking time out of your day to join us and interact with our presenters. Before you leave today, we always ask that you participate in our short survey. You will find a link to it directly below the closed captioning pod on the right-hand side. It just says survey. If you click on that, it will open up our customer satisfaction survey. We do want to make sure that we're providing the best webinar experience that we can, as well as how we disseminate that information out to you, our audience. So if you could take a few moments to complete that survey, we would definitely greatly appreciate it. You will see here momentarily, Tyler will be putting in the chat pod our social media outlet links, such as, I apologize, our Facebook, LinkedIn, and Twitter. So if you are not following us on there, please make sure to do that. Also, we will be putting up links to our podcast. We'll have a couple more podcasts that will be launching before the end of the year, as well as a link to our website where you can find all of our no-cost webinars, reports, and success stories that we are constantly putting out through the Forensic Technology Center of Excellence. Again, thank you everyone for attending today's event. We definitely appreciate your attendance and your support, and we look forward to seeing you in our next webinar. We hope you have a great afternoon.